Hey everyone, welcome. In this explainer, we're diving into one of the most powerful ways to solve complex differential equations, the series solution. And we're going to be using Chapter 6 of Shepley L. Ross's incredible textbook, Differential Equations, as our guide.
Yeah, we're going to stick pretty close to the logical flow of this classic text. It's just a fantastic way to build a really solid understanding, going step by step from the basic ideas all the way to some pretty advanced stuff.
So let's start with the big problem, right? We have all these great techniques for solving differential equations, but what do you do when you run into one that just doesn't have a simple, neat solution? A ton of the most critical equations in physics and engineering are exactly like this. So what tools have we got?
Okay, here's our game plan. We're going to start with why we even need series solutions in the first place. Then we'll see how they work for the nice cases, which we call ordinary points. After that, we'll tackle the real beast, singular points, with a powerful tool called the Frobenius method. And finally, we'll see it all come together to crack the famous Bessel's equation.
So, first things first, why bother learning a whole new method? Well, we turn to series solutions precisely when our usual tools just don't cut it. This approach unlocks a whole new, and frankly, much more interesting, class of differential equations.
And the hero of this whole story? It's the power series. You can think of it like a polynomial that just goes on forever, which lets us approximate all sorts of functions. By assuming our solution is a power series, we basically change the problem from calculus to algebra, just hunting down the coefficients one by one. Okay, so let's actually put this idea to work. We'll start with the most straightforward case, which you'll find right in section 6.1 of the textbook, finding solutions around what are known as ordinary points.
So what exactly is an ordinary point? It's just a spot where the coefficients in the equation are, let's say, well-behaved. The technical term is analytic, which really just means they can be described by their own power series. For us, that's the green light. It tells us our standard power series approach is going to work just fine. And what you get is this really clean step-by-step process. You just assume the solution has that power series form, take its derivatives, plug everything back into the original equation, and then solve for the coefficients. It's a surprisingly elegant way to unravel the problem.
But what happens when the equation isn't so well-behaved? This is where things get interesting. I'm talking about points where the coefficients go crazy. They might blow up to infinity or become totally undefined. We call these singular points, and our basic method usually just falls apart here.
This table really lays it all out, doesn't it? At ordinary points, it's pretty much smooth sailing. But once you hit a singular point, the behavior of those coefficients gets erratic, and our whole assumption breaks down. We're definitely going to need a bigger boat.
So to tackle these tougher spots, we have to upgrade our toolkit. Let's head over to section 6.2 and meet the powerhouse it introduces, the method of Frobenius. It's specifically designed to handle a special class of these singular points.
Now, here's the key insight. Not all singular points are equally bad. The Frobenius method is built for what we call regular singular points. These are places where the problem is, let's say, mild enough that we can still find a solution if we just tweak our series approach a little. And right at the heart of this new method is something called the indicial equation. You can think of it like a diagnostic tool. We pull it straight from the differential equation, and its roots, R1 and R2, literally tell us what our series solution has to look like near that tricky point. It's the key that unlocks the whole thing.
So here's the upgraded process. We start with a slightly different series, the Frobenius series, which has this extra little r in the exponent. That's the secret sauce. After we substitute it in, we get to the most important new step, finding and solving that indicial equation to figure out what r can be. Those roots then become our roadmap for building the final solutions.
All right, so we've got this awesome new method. Let's really put it to the test by taking on one of the most important differential equations in all of science and engineering, which is covered in section 6.3, Bessel's equation.
And here it is. Now, if you look closely at its coefficients, you'll find it has a regular singular point right at x equals 0. That makes it the perfect candidate for the method of Frobenius. This thing was a beast to solve with older methods, but for us, we now have exactly the right tool for the job.
So why do we care so much about this one abstract-looking equation? Because this thing shows up absolutely everywhere. As you can see from these examples listed here in both English and Arabic, if you want to understand how a drum vibrates, how heat moves through a pipe, or how radio waves travel, you need to solve Bessel's equation.
And this is where it gets really cool. The solutions we find aren't things we already know like sine or cosine. They're a whole new class of functions called Bessel functions. By solving this 1DE, mathematicians didn't just get an answer, they discovered an entirely new set of tools for describing how the physical world works.
Wow. Okay, let's just take a step back and look at the journey we took. We started with a tough problem, equations that wouldn't budge with standard methods. We built a tool for the easy cases, the ordinary points. Then we leveled up to the Frobenius method for the trickier, regular singular points, and we used it to conquer a cornerstone equation of modern science.
And that, right there, is the real power of mathematics. It's not just about solving problems. It's a framework for describing the world in incredibly deep ways. So now that you have these tools, the real question is, what complex systems are you going to model and understand next?